Welcome to the Carbon Emissions Assessment video from the Kearney Energy Transition Institute. Here you will find a summary of the main concepts of this FactBook published in 2022. This FactBook is Volume 1 of the Carbon Emissions Management series. You can find more about it in our website. This video is structured in 4 chapters. We first look at the atmospheric mechanisms that control the global temperature, providing an overview of the main sources of carbon emissions at the global scale, including carbon dioxide and methane. We then look at the recent technologies deployed to measure and monitor carbon emissions at a global scale, prior to presenting the concept of life cycle analysis that provides a methodology to assess overall carbon footprint of human activities. In the last section, we present selected use cases from the energy sector. The temperature of the atmosphere varies, with the energy balance resulting from incoming solar radiation and the emitted infrared radiation. Before the industrial era, the atmosphere had reached an initial equilibrium when incoming and outgoing fluxes were balanced. This stabilized the global average surface temperature with a radiative forcing close to zero. But this process is dynamic as radiation fluxes are transiting the atmosphere and greenhouse gases are constantly emitted. Anthropogenic activity has increased the emission of greenhouse gases, producing a decrease of emitted infrared radiation, retaining extra heat in the atmosphere, which in turn creates a positive energy imbalance or positive radiative forcing, which is translated into global warming. Because of the inertia of the system, it takes several centuries to reach a new equilibrium. This new energy balance reflects a new average temperature, likely superior to the previous one if the radiative forcing is positive. Let's now look a little closer at the atmosphere. The properties and dynamics of the atmosphere are essential to understanding the cooling and heating effects on Earth. First, let's talk about the atmospheric albedo, which is the diffuse reflection of the solar radiation in the atmosphere and is dependent on cloud cover, influenced by humidity and atmospheric circulation. Aerosols, which are small particles in suspension and generally have a cooling effect. These particles can come from fossil fuel combustion, volcano eruptions, dust, and even sea salt. Dark aerosols or black carbon also exist, and are made of smoke, industrial ash, or soot, and unlike other aerosols, have an important warming effect. There is also the surface albedo, which depends on the Earth's surface cover. Depending on the type of cover, the reflective properties change. For example, ocean albedo has a lower reflection than sand cover. These atmospheric and surface albedos partially reflect incoming solar radiation and contribute to cooling the Earth. The atmosphere also receives gases produced by natural and anthropogenic processes, participating in the retention of the infrared radiation in the lower atmosphere. These gases have a greenhouse effect, thus warming the atmosphere. Some gases, such as carbon monoxide and nitrogen oxides, are not greenhouse gases but become tropospheric ozone when combined with other gases under the effect of light. Anthropogenic emissions accumulate and increase their concentration in the atmosphere, land, and oceans. Now that we have some basic concepts, let's move on to understand more about which gases we are talking about. Greenhouse gases are emissions emitted by natural and anthropogenic sources. The main gases that have a greenhouse effect are carbon dioxide, methane, nitrous oxide, fluorinated gases, and nitrogen trifluoride. The vast majority of carbon dioxide and methane are emitted by human activities. All human activities are greenhouse gas emitters, and the energy sector is by far the largest emitter, accounting for more than 40% of total greenhouse gas emissions, participating mostly with carbon dioxide and methane emissions. It is important to note here that this graph does not dissociate the energy needs from sectors such as industry or transport. This means that industry emissions include the energy and electricity emissions from this specific sector. So anthropogenic activities are responsible for carbon dioxide, CO2, and methane, CH4. Stacking up to 93% of overall emissions. And this represents about 52.5 gigatons of CO2 equivalent. Now we'll take a deeper look at these various sectors to better understand emissions. When looking at CO2 emissions, energy systems are responsible for 33% of these, mainly emitted by electricity and heat production. In other segments, we see how some industrial processes also participate with CO2 emissions. About 27% of the global CO2 is coming from metals, chemicals, and other processes. Transport emits 23% of the CO2 emissions primarily from road transportation, while buildings produce about 7% of emissions, mostly because of heating systems. If we zoom in on methane emissions, energy is also responsible for 7% of global methane emissions through petroleum refining and fugitive emissions from the oil and gas industry. while the waste industry emits 22% of these emissions and buildings emit 3%. Lastly, agriculture, forestry, and land use changes are activities that emit mostly methane, in particular from roaming livestock such as cattle, representing about 42% of these global emissions. As we saw in the previous slide, emissions from energy systems represent about 40% globally, while a quarter of the global emissions are produced by industries, followed by transport with 18% and then AFOLU and buildings. All these estimates are based on considering gases' lifetime of 100 years. To summarize, the largest CO2 emitters are electricity and heat production as well as road transportation, while the largest methane emitters are livestock and oil and gas fugitive emissions. Now that we understand the type of gases and where they come from, let's talk about how we measure these gases and the importance of gas lifetime in the calculations. First of all, why do we need to assess emissions? Emissions are measured to quantify the impact of GHG by estimating gas concentrations in the atmosphere and the resulting difference between the incoming and outcoming flows. How are emissions assessed? There are multiple metrics available, but when following UNFCCC standards, emissions are measured in global warming potential GWP100 and its related CO2 equivalent. These metrics allow for the comparison of the effect of greenhouse gases to the effect of CO2 over various time horizons, as they take into account the different properties of gases, such as lifetime in atmosphere, wavelength, and energy absorption. Choices of time horizon affect the results by a factor of up to 10. Understanding the differences between types of metrics is necessary to correctly interpret their values, which can vary by a factor of about 200 depending on the type of metric used. For example, methane is more efficient at causing global warming than many other gases. In the first 20 years after being released into the atmosphere, methane is 84 times more potent at trapping heat than carbon dioxide. Over 100 years, methane is 28 times more potent than carbon dioxide, so the methane warming potential decreases with time. In other words, 1 kilo of methane is equivalent to 84 kilos of CO2 if measured in 20 years, and only 28 kilos of CO2 if measured in 100 years. Now that we understand some of the concepts, let's briefly cover how we can measure and track global carbon emissions. First, let's define the global carbon cycle, which is estimated by using a multitude of data sources. To calculate this cycle, data from emissions from fossil fuels and industry are added to the emissions from land use change. Then, the CO2 concentration growth in the atmosphere is measured and the ocean and land sink estimated. Finally, the budget imbalance is the difference between the estimated emissions and the estimated changes in the atmosphere. Each of the items of this equation rely on data sets that are a measure of imperfect data. So how accurate are these measures? Data accuracy depends on the way it is measured, and the uncertainty depends on the sensor type, which could be in situ or remote sensing, the sensor placement, which corresponds to the distance from the measurement point to the gas source, and finally, the calculation technique, which estimates the gases emitted with a certain degree of uncertainty depending on the types of models used. As mentioned, the data used to estimate the global carbon cycle has a degree of uncertainty. Many new technologies are being developed and deployed to increase coverage resolution, accuracy, and frequency. Among these technologies, microsatellites, high-resolution satellites, and satellites using active and passive sensors are playing a central role. Drones and airplanes are also being used to increase the accuracy of models and the reach of sensors. To limit uncertainty, technological progress is integrating measurement and monitoring systems. Integrated system means complementing top-down monitoring with bottom-up sensors. These systems rely on sensors with a wide spectrum of frequencies, ranges, and resolutions. Global GHG monitoring systems have matured but still face constraints and challenges, such as coverage compliance, accuracy, standardization, and regulations. Now let's walk through the concept of the emissions life cycle. Life cycle thinking is a concept promoting a comprehensive approach to evaluate the impacts of a system. It can be applied to assess economic, social, and environmental impacts. Life cycle assessment, also known as LCA, is an internationally standardized method to evaluate the environmental impact of a product or service and define mitigation strategies. LCA is defined under the principles and framework of ISO 14040. In a product's life, activities are linked by physical exchanges, and these are related to the environment through elementary flows such as materials, emissions, or energy. There are a variety of approaches to LCA depending on system boundaries. Cradle to grave, Full LCA from resource extraction to end-of-life phase. Cradle to gate, assessment of a partial product's life cycle from resource extraction to the factory gate. Cradle to cradle, specific type of LCA where the end-of-life step is a recycling process. Gate to gate, assessment of the impact of a single production step or process in the entire production chain. A specific LCA is defined for transport fuels and vehicles. Well to wheel, which is broken down into well to station and station to wheel, or well to tank and tank to wheel. LCA is structured through 4 complementary steps, starting with the definition of the intent and scope of the assessment. Then, the life cycle inventory is generated by producing a compiled inventory of elementary flows from each stage of the product's life cycle. The third step corresponds to the life cycle impact assessment, which classifies the results into environmental categories and impact characterization. Lastly, the results are interpreted by identifying, quantifying, checking, and evaluating these. LCA has various levels of application, and among these we can find the following. Original product-based scope, which corresponds to the traditional use of LCA to assess and improve specific product systems, such as process optimizations, supply chain management, marketing, strategic communications, or eco-design. Organizational company LCA, broadly used by companies to determine the key drivers of the environmental impact of their product portfolios. Consumer LCA are based on environmental scorecards that analyze current and future consumption patterns and lifestyles. Lastly, LCA is also used for national-level assessments, which are top-down studies of national economies aiming to highlight crucial drivers of environmental impacts, such as housing, mobility, or food. All these assessments have the same objective: to identify environmental hotspots for product improvement, corporate sustainability strategy, consumer lifestyle, national sustainable consumption, and production policy setting. As we have just seen, LCA has various applications, and the definition of scopes can be challenging. Let's now move into the last section of this video and discuss the computation of an LCA. LCA computation is complex and dependent on several parameters. LCA calculates carbon emissions produced at each phase of the product life cycle, and, for each of these phases, corresponds a specific service requirement. Energy consumption emissions represent the quantities of energy required and their combustion emissions from different sources that can be used to provide a given service. LCA computation also includes any other process emissions required for production, and finally, all other eventual emissions intentionally or unintentionally leaked. The process and fugitive emissions are uncommon compared with the energy emissions. They are also called mobile and stationary combustion emissions. Into this computation, several parameters enter into play, such as volume of production, distance of transportation, composition of materials, type and mix of energy source, or emission factor of fuels. Other parameters could affect the release of emissions, such as physical or chemical reactions, the type of processes, the equipment, or even the location. As mentioned, uncertainties around emission factors have a wide range of variability, and boundary conditions are key to optimizing carbon emissions reduction. As an example, let's compare the emissions uncertainties among products. For petroleum products, uncertainties are lower, conforming to tight specifications and measurements that are made at a small number of refineries. On the other hand, coal products have very high uncertainties, as coal is sourced from mines with a very wide range of carbon contents, calorific values, and equipment specifications. Biomass uncertainties are, as with coal products, subject to high uncertainties because of the wide range of carbon content of the material or their calorific values. For biomass, as for all fossil fuels, emission factors here do not include the full life cycle of biomass. Negative emissions are not considered. Now, let's take a look at the life cycle assessment of selected activities. For this, the carbon emission is estimated following the equation we defined previously. First, let's briefly look at primary metals and each phase of the primary metals life cycle. For each phase, service requirements such as the production volume, metal or grade, or size mine are parameters taken into account, along with their energy needs considering the efficiency of drilling or from the extraction process and the type and quantity of energy used for each step of the process. This logic is repeated in each of the steps of the production process. When comparing different metals, there are large differences between metals, and many primary metals used for low-carbon energy technologies have very large footprints. For example, gallium, which is used for CIGS solar cells, is 150 times more intensive than iron. But this technology represents a very small share of the solar photovoltaic market, which is dominated by silicon-based systems. Parameters are rarely fully considered when estimating these carbon emissions. Let's also look at solar PV and its life cycle, where manufacturing represents 89% of the carbon footprint if the solar panel is produced from multi-silicon, in Germany for a 20-year lifetime and a load factor of 12%. Factors such as the electricity mix, panel location, and load factor have an impact on the carbon footprint during the production phase. As an example, a PV panel produced and operating in China has a carbon footprint 58% larger than one in the European Union. Let's now look at the production of lithium-ion batteries. The process for producing lithium-ion batteries goes from the material production to the recycling phase during its end of life. The materials production phase is the most carbon-intensive, representing 80% of the battery footprint, in particular the electronic parts, the cathode and electrolyte. The battery capacity is also a factor directly related to the carbon footprint. Doubling battery capacity quadruples its carbon footprint. Now, if we look at the life cycle of a battery electric vehicle, without much surprise, the biggest part of the carbon footprint comes from the manufacturing phase, as we saw above. Depending on the car size and battery capacity, the use of battery electric vehicles can be detrimental from a carbon footprint perspective. The ideal use of a battery vehicle requires the electricity mix to be below 120 grams of CO2 per kilowatt hour and the car mileage usage above 39,000 kilometers. Lastly, let's take a look at the life cycle assessment for electricity sources to understand their carbon footprint during the lifetime of these installations. Low-carbon electricity sources like nuclear, renewables, biomass, or green hydrogen have a carbon footprint under 128 grams of CO2 equivalent per kilowatt hour, and as you can see, this is way below fossil fuel electricity's footprint. Power from coal has the largest footprint, reaching more than 1,300 grams of CO2 equivalent per kilowatt hour, while natural gas is around 560 grams. It is important to note that LCA results for various electricity sources show high variability in their carbon footprint. This is the case for technologies such as solar PV, nuclear, or power from green hydrogen. This variability needs to be taken into account when assessing other value chains embodying these sources of energy. In terms of carbon footprint, coal is 7.5 times higher than low-carbon electricity, while gas is about 3.5 times higher. Thanks for watching this video. If you would like to learn more about this topic, visit our website and discover the full carbon emissions assessment, FactBook, and much more.